Now, as we go into Unit 2 in our first lesson, dealing with ratio, proportion, and variation, I think you have the pattern that we want you to follow. Label your examples, write them out, show the work on the other side of the page. I won't keep repeating that, but that's what's expected. Okay. Now, writing ratios will be something we do. Unit pricing, you don't have to write these down yet. Solving proportions, direct variation, inverse variation, joint and combined variation. You'll get these topic headings as we get to them. And then writing a ratio. A commonly used mathematical concept is a ratio. A baseball player's batting average is a ratio. The slope or pitch of a roof of a building may be expressed as a ratio. Ratios provide a way of comparing two numbers or quantities. Now, a ratio is a quotient of two quantities. And they're showing you three ways to write a ratio. This is one way, this is another, and this is a third way. You want to have these in your notes. Now, a ratio is a quotient. And the best way to describe a quotient is as a fraction that we mentioned earlier. When ratios are used to compare units, the units should be the same. So if you're comparing hours and minutes, those are not the same. So you have to convert the hours to minutes, or feet to yards. Yards, 3 feet in 1 yard. Again, if you're not sure of any of these, ask. And your textbook does give lots of good information. Now here is our first example. Again, write this up in your notes, and I'll do it for you here. Now, when you write a ratio, you write it, the first one is on top, the second one is on the bottom. But notice, this is 8 hours to 2 days, so that wouldn't be the proper way. We would have to convert the days to hours by multiplying each day as 24 hours. Now we can do some cross-canceling. For instance, 2 goes into there once, 2 goes into there 4 times. So we now have 4 over 24. 4 will go into there once, 4 will go into there 6 times. So in simplest form, our ratio would be 1 to 6. And there it is. Now, unit pricing, and we see this throughout the supermarkets and places where what does an ounce of something cost? And if you have 9 ounces at a certain cost and 15 ounces at a certain cost, you might wonder what's the better deal. So this is where unit pricing comes in. Now here we have a 16-ounce box of cereal, and this is our second example. Write that. So it's $3.36, and we're going to divide that by 16 to find the price of a single ounce. Well, I have my calculator, and I go 3.36 divided by 16, and I get 21 cents. Now notice, this is the way to indicate 21 cents as dollars, and then 21 cents as cents. Notice the placement of the decimal. And there's the work. Now, we did this in our previous unit where we had proportions. 1/2 equals 3/6. And we talked about the extremes, the 1 and 6, and the means, 2 and 3. And we said the product of the extremes equals the product of the means. So if we did that, let's just show it to you. Nope. We went back one slide. Let's do it here. This would be 6, and this would be 6. So once again, there's the proof. And remember, you can't have a denominator that says 0. That's what they're giving this qualifier for. And we've already talked about terms, extremes, and means. Just a little review. And we've done the cross products already, and there's our statement that we already have in our notes. Now, this, as I mentioned in the earlier unit, can be used to solve when we have an unknown, that is, solving proportions. So this is example 4. We have 4/5 equal 22 over x. And we want to solve for x through cross multiplication. So this is going to be 4x. And this is going to be 110. And we divide both sides by 4 here using a little algebra. And we get x equals 110 divided by 4. And we get 27.5. So one of the kinds of things you're going to be asked to do in proportions is to solve for the missing letter here, x, the missing value. And we do that by cross multiplication and then solving that little equation. Which they will show us right here. Now they're getting 55/2, which reduces to 27/5. You can leave it this way too. Alright, we're now going into some other background material, direct variation. And I would like this to become so automatic that when you see direct variation, you write this equation. Y equals kx. This is the general formula for direct variation. Sounds like a good quiz question for me. What is the formula for direct variation? And they have it here, of course. Now, if you want to solve it for the letter k, what you would do is divide this side by x. Divide this side by x. Here the x's cancel out and you get k equals y over x, which is this one. Now, what is the letter k called? It has a special vocabulary term associated to it. K is the constant of variation. Sounds like another good quiz question. So again, pause is needed. Now, one of the things we're going to be doing is solving a variation problem. Step 1, write the variation equation, which is y equals kx. Substitute the initial values and solve for the letter k. Rewrite the original variation equation with the new value of k, and then substitute the remaining value to solve for the unknown letter. and find the required answer. Well, these are the steps. You can write them down if you'd like, but I will show you them in some detail here. Okay, step 1. This is a direct variation. This is for example 5. And that equation is y equals kx. Alright, now substitute what y is. Y is 45. We don't know what k is, and x is 30. Now, solve for k by dividing both sides by 30. And we get k, I should have left a little more room here, can simplify into 3/2. Now we're going to write our new equation of direct variation, which will be y equals, we have found what k is, which is 3/2, and then x. So that's the third step. Now, they want us to find the value of y here when x is 12. So we write it, y equals 3/2 times 12. That's our new x value. So 2 goes into there once, 2 goes into there 6 times. So now y equals 3 times 6 is 18. Those were all the steps. Let's review them. Step 1, direct variation, write your equation. Y equals kx. I'll put a 1 there. 2, substitute the values given, the y and the x, to solve for k. We now have solved for our letter k, which is this. Write the equation, now your new equation, in which you put the new value of k. Y equals our new value of k, x. Then they're going to give you a new variable, x. Find out what y would be. So we put it, y equals, we know the value of k now, we know the value of x. We do any cross-canceling from our previous unit, and we get y equals 18. So this is the protocol in solving direct variations. And there are the steps that we talked about. And then we end up with our answer, y is 18 when x is 12. Again, pause as long as you need. Now, sometimes when they modify a direct variation, instead of x being a regular kind of x, it's the nth power they use of x. And we just indicate that as raising x to some exponent. Okay. So, let's do example 6 now. PP says the area of a circle varies directly as the square of its radius. Now, diagrams are nice, so let's just make a little diagram here. So, this is my circle. This is a radius from the center to the outside point. And now we're looking for area. So if A represents the area and R the radius, then for some constant K, we get area equals the square of the radius. And that's where we have our exponent associated. Now, some of you may recognize this formula, but take some notes on it. What is the value of K? Well, it's going to be, if we solve for k, it would be area divided by r squared. Okay, now this is area. Any hints yet as to what k would be? Well, as we may or may not have mentioned before, it's pi. The formula for area is area equals pi r squared. So pi is our constant of variation in the area formula for circle. Okay, let's go on and have some good notes here. Now, inverse variation. Again, when you see the words inverse variation, the formula that comes to mind should be this: y equals k over x. Now, if we want to solve for, and then this is what you're going to write as the formal equation for inverse variation. Now, if you want to solve for k, you do so by multiplying both sides by x. Here the x's cancel out, and we get k then equals xy. K equals xy. But this is the official formula, not this one. This is solving for k. We want what y equals. Y equals k over x. And if x is to some power, we just put the power there. And that's what they're showing us. 2 items of background information on one slide. So get your notes and we'll move on. Now, example 7. Here they talk about inverse variation. The weight of an object above Earth varies inversely as the square of its distance from the center of the Earth. Now, to write this formula, let's just do that up here. We have the weight, instead of y equals kx, and then this is going to be x squared here. We're going to write this weight of a person equals k that we don't know, and then to the distance from the center of the Earth, that's squared. So often what we do is we know our general formula for inverse variation, but then we qualify this formula by putting in the letters of our search where we're applying this. This makes a little more sense. Weight, distance squared, and we have to find out what k is. So here are the items. I'm going to go to the next slide to save us a little time because this one is worked out very well on the next page here. Oh, went ahead too much. Let's go back here. So there's our formula that we've done. And now they're saying that to find out what our k is going to be, we put in the weight of a person at 57. The distance from the center of the Earth is 6,700 that we're going to square. Now, they're not showing this, but let me show it to you. How do we get what k is? Well, in a way, you can look at this as a fraction, 57 over 1, and k over this. And if so, it becomes a proportion that you can cross multiply. So it's just 57 times this. I went out to shovel a little snow here, but back to this. So this times this is what they have here. They didn't get an answer, just that's what K is. So when you do your inverse variation here, K is this, you're going to put that in your calculator, and then divided by this squared, which is the new distance, a little closer. So the person now weighs almost triple. Okay, so again, weight is not a fixed amount. It's a kind of ratio compared to where you are from the center of Earth, distance squared, and then by this K factor. Okay, let's go on. Now, sometimes you can have I should clear that up here too. You can have what they call joint and others combined variation. So joint is that instead of just being one variable in the numerator, let me give you an example of this. It would look like this. It would be y equals k, and then you might have x, and then let's say another letter, s or something. And then it could be a combined variation where you have part of it. Remember, k is always in the numerator. Part of it would be in the numerator, but you might also have a variable in the denominator that would be inversely related. So, again, we're not giving you formal formulas here, just the two that we had earlier. But we'll see some examples of this as we go on. Okay, so here they're saying M varies jointly as x and y. So the k is in the numerator, x and y. This would be a joint variation. And this would be a variety. Combine something in the numerator and something in the denominator. You have to read the example carefully. And by the way, we are calling those examples. So going back, be sure you put 8 pp and 9 pp for this one. And they've asked you to write what is in words into a symbolic representation. The strength of a rectangular beam varies jointly as its width and the square of its depth. If S represents the strength, W the width, and D the depth, then for some constant K would look like this. So take a moment. You want to illustrate what one looks like. Okay, now we're into actually writing these problems out. And some are in the book and some are not. And I've tried to distinguish that. So you want to write everything down. This will reflect good notes. Write a ratio for each word phrase. Again, you might try this. Take a moment. And it would be 5 hours goes on top and 3 hours in the denominator. Now, we did one like this, 6 hours to 3 days. But we need to have everything in hours, so we're going to go, days have 24 hours. So here, we can do some canceling. So we end up with 2 over 24. We can take a 2 out of each one, which is 1 out of 12. And there we see all the work supported. Now, if you have a textbook, all this work is in the textbook as well. Okay, here we have peanut butter. I like peanut butter, which is the Best Buy. So what you would have to do is set this up in the following way. 1.78 divided by 18. What would that be per ounce? 2.97. What would be that per ounce? And 3.98. What would that be per ounce? Okay, we'll do some figuring and get back. So once we do the division, we see that comparing these numbers, 0.098, 0.1, so this one's definitely not, and this is 0.099, so this would be your best buy. That is the 18 ounce, so that's not usual. Usually the larger quantity is your better buy. Okay, let's take a look at what they have here. And there they go. Now they're doing some rounding here, but 18 ounces is your best buy. Okay, here we have a proportion you are to solve, and it's rather straightforward if you recall the recipe. We're going to multiply these together, the extremes, and get 9x. We're going to multiply the means, and I get 5 times 63 is 315. Then I'm going to divide both sides by 9, and I get x equals 35. So straightforward using the cross product method here. And there's our answer. Now here's a little bit of an upgrade where we need to spend a little more time and use our algebra skills. And keep in mind we can put these in parentheses here. So work this with me. Cross multiply. So it would be 3 times the x, which is 3x, and 3 times the negative 2, which is negative 6. 5 times x is 5x. 5 times 1 is 5. I'm going to subtract 3x from this side, and I get 2x on that side. I'm going to subtract 5 from this side, and then subtract 5 from that side gives me a negative 11. Divide both sides by 2, and I get x is a negative 11 halves, which is, if you want to put it in fraction form, a negative 5 1/2. So they should accept it this way or this way. And they're showing it as negative 11 halves. Okay. Again, you can pause any of these things to look at it in more detail. All right, now this is actually number 6 in your booklet. So just change this to a number 6 here. You can do that in your booklet if you like too. I'm going to do it here. So this is actually number 6. Now, I have a background in biology and ecology. That's what I taught basically, but also math. And I did do a project one time on a field assignment where we went out to tag eels. And what we did is we were in our hip boots and nets, and we captured the eels, tagged them as they were going from the stream into the... And we can see it here on the solution. They do a nice job. That we tagged 300 fish or eels or whatever. I think we only tagged like 12 or something. when we did it. And then, do we know how many eels or fish were in the lake? And the answer is no. So we put an X there. Now it's critical of how to set these proportions up. The ones we tagged, and then there were an unknown number of eels. Then another time we went out, and when we captured, let's say the fish, we'll stick with this example, we got 5 fish that were tagged out of 400 that we saw or caught as we were releasing them. We just wanted to see if we got a fish that was tagged. So we had a sample of 405 were tagged. But originally we tagged 300. So tag is to the number of fish we didn't know on that first day. The ones now that were tagged out of the number that we caught, our sample. So we're going to cross multiply here. And they're putting 5 times x is 5x. 300 times 400 is 120,000. And now we're going to divide both sides by 5. And you can show this in your work. And then we found, or we're estimating, that we have in this lake 24,000 fish. And this is a tool that's often used by wildlife service that is interested in determining populations. They tag a certain number, but they don't know what the whole number was. Then another time they capture 400 and 5 of them are tagged. So tagged is to the total, tagged is to the total. We're using the cross multiplication, the product of the extremes equal the product of the means, and then solving for our unknown. They do this very well here. In this next slide, they're telling us of direct variation, the formula that you should use, and we underline that. And we say it can also be shown this way, but this is the formula that we're saying is the official formula of direct variation, y equals kx. So for example 6, we now are asked to solve what is the relationship. Well, number 1, we know it's direct variation, so we write the direct variation formula, y equals kx. For step 2, we put in substituted values for y, which is 50. We don't know our k. We're going to solve for k. And x is 20. Number 3 is we solve for k by dividing both sides by 20. And we then get k equals 5/2. We then write the formula again as our equation of direct variation, y, where we put our value of k in, 5/2, and then we want to solve it for x now, where x is 14. So we put the 14 in there. So our solution then is we can cancel 2 goes into their 1s, 2 goes into their 7. Y will be 35. So again, reviewing this, and you could use this, as we mentioned earlier, as a model to solve these. Went back for some reason. There we go. And there's our answer, 35. Now, often there are other kinds of examples, and I believe this one is in your booklet as well. And what kind of relationship? Take a moment to look it over. It's directly proportional. So this will be y equals kx. But since we're using what they call Hooke's law, We may want to change some of the letters to reflect this better. It says the force, so we're going to put here Y as force. We can use the letter F. We don't know our K. Stretches a certain spring this much, but it's directly proportional to how much it stretches. So this will be distance. So now we have to do some substitution because we want to solve for what K is. Now we say a force of 150 pounds, you don't know K, stretches it 8 centimeters. That's our distance. So we're going to divide then both sides by 8, and we get K equals, let me use my calculator here, 150 divided by 8, and that's going to be 18.75. 150 divided by 8. So our new equation is going to be, let's use F still. We know that K now is 18.75, and we're going to apply a force of 400. So we don't know what our distance is, but that's what we want to solve for. So I have to take the F away here and put there 400. So now we're going to divide both sides by 18.75 because we want to solve for D. So I'm going to put in there 400 divided by 18.75, and I get a distance of about 21, and a repeating fraction, which is 0.333, which is 1/3. Here they're showing us a nice example of it. There's the scale stretching 8 centimeters, and then later they're listing it as an improper fraction, but this is 21 1/3. So that's a good one. All right, let's go on to our next slide here. So here we have a body at rest. Varies directly as the square of the time, so x would be squared here. But to make this a little more easy to pick out, the distance that a body falls, k, to the square of the time, we're going to use t squared. So again, we have to solve. It says if a skydiver falls 64 feet, so 64 equals k. Now distance is going to be, or I should say time, is 2 that we're going to square. So you have to be careful here. So this becomes 64 equals k times, we need to do this first, 4k. We're going to divide both sides by 4. So we get k equals 16. Now, how far will he fall in 8 seconds? Well, we're going to have distance equals our new value for k, which is 16, and the 8 is going to be squared. Now remember, it's distance here equals k times time squared. So time is 8 seconds, so we square the time. So this is going to be 16 times 64. Put that in your calculator and mine. 16 times 64, and that is 1024 is our distance. Okay, let's check this out. And 1024 is correct. And again, in our text, they give a great detail of how to solve these. And this is what we're illustrating. And they also give nice pictures, too. Okay, now we did one like this, but I'd like you to add some words now, if this is not written up in your book here. So when space vehicles go around the Earth, this is the center of the Earth here, it doesn't go around in a circle. It goes into sort of a oblong circle here, where sort of ellipsis they call this. Not to confuse it with our three dots, the ellipsis, it's spelled a little bit differently. It's elliptical, that is sort of an oblong circle. So we have this distance here as distance 2, and this distance here as distance 1. So here they would have a higher weight, if you recall. Now the shorter distance that a spaceship is from the Earth's center compared to when it's in its elliptical orbit is going to cause the person to have more weight, where here this is a longer distance, so they would weigh less here. And I want you to be a little, for just as historical reasons, the shorter distance is referred to as the perigee, and the longer distance is referred to as the apogee. So in the ellipsis, this type of ellipsis, the longer distance, the apogee, the shorter distance, the perigee. Sounds like good quiz questions to me. Okay, so let's set this up. And since I've been doing a lot of these, and we did one like this, let's have the book do it here. And again, it's not to scale. So this is an inverse variation. So the weight, we did one earlier like this, k over d squared. Here we get d squared. There's the weight. So we multiply, this is like over 1. We cross multiply, get this as k. Put this as our new k over our new distance, which is shorter here. So they're going to weigh, in this case, 153 pounds. So again, you need to understand what they're asking here, so that when I ask the quiz question about this example, and, have this written up in your notes, you have the values there. These are the words we're looking for, perigee and apogee. And then these are the weights. So at the shorter distance, when you're closer to the Earth, you're going to weigh more. That would be 153 pounds. And at the apogee, the further distance from the Earth, you weigh less. There it's 57 pounds. Okay. Now, here is a joint variation problem. The strength of a rectangular beam varies jointly as its width and the square of its depth. If the strength of the beam 2 inches wide and 10 inches deep is 1,000 pounds per square inch, what is the strength of a beam 4 inches wide and 8 inches deep? Well, again, it's a compound joint variation. So S is what we're looking for, is strength. We don't know what K is. We know the width, and we know the diameter squared. We plug that in, and we find that K is 5. Take a moment, pause to write these values down. Now, with our new value of 5 for K, we then want to find the strength of the new beam when we put W as 4 here. There's our 4. And our D is 8 that we're going to square. Now you want to put this in your calculator. Remember, you square this first. And then this is 20 times 64 will give you 1,280. Wow. So there's a lot of strength in that beam. Okay, this is one that is body mass index, BMI, and this is true. So let's just read it together. Is used by physician to assist a person's level of fatness. BMI varies directly as an individual's weight in pounds, and inversely as the square of an individual's height in inches. So we need to find K, and we'll show you this, and watch it carefully. So a person who weighs 118 pounds and is 64 inches tall has a BMI of 20.25. Usually we round to the nearest whole number. Now, Grady Sizemore of the Cleveland Indians weighs 200 pounds and is 6 feet 2 inches tall. So we're going to have to convert this to all inches here to put in our formula. Find the body mass index here. This is our last example, so we'll use the text here. So there's our body mass index, B. K we don't know. We know the weight, and we know it's divided by the height squared. So substituting our values into the formula, just copy this in. Now notice this is over 1, so we can find out what K is. K will be this divided by the 118. So our K then is 703. So putting 703 into our formula, where this is his weight, and we had to convert 6 feet 2 inches to 72 plus 2 inches is 74 inches squared, is this, and they're asking us to the nearest whole number. So the body mass of Grady is 26. Rounding that off to the nearest whole number would make this 26. Alright, this will wind up our lesson. Again, the nice thing is if you have to go back to look at something, it's available. You want to have good notes so you do well on your Open Notes quiz.